Kang from KIAS will tell us about new physics in Di-Higgs event.
Sorry for the delay. Thanks for the organizers. And here's my talk. I will talk about the new physics chance in the boosted Di-Higgs plus missing energy signature. And my talk will contain three parts. The first part I will talk something casual about the Higgs physics status within and beyond the standard model. And the second part is about the signature, boosted Di-Higgs boson plus missing energy. And this is somehow it's a new signature. And eventually I will talk about something about the model. And the first and the third part, which I'm good at it, but the second part is not my good part. So probably we'll talk fast. We know the Higgs. When we are talking about the Higgs in the standard model, we know they have two phases. The first phase is that it's very important. You can say that it's actually the key role for electroweak unification. And the second one is that it's a mass source for all the standard model particles except for the selenium neutrinos. But we know that the neutrino mass probably is also related to the Higgs field. And the third part is that Higgs, it's talking about the second phase, the bad phase somehow. It's a troublemaker because it leads to the gauge hierarchy problem. It means that everybody knows that the weak scale is not stable on the quantum correction. But this bad phase actually, for the theoreticists, it's also a good phase. It's give a much chance to play. So here, we talk about the Higgs. It's a window to a new world. This is the top one motivation for Higgs beyond the standard model. The hierarchy problem should be addressed. For example, by supersymmetry and compositeness. And this is theoretical motivation. And there's some other phenomenological motivation. For example, the neutrinos are massive. This is a definite signature that we should go beyond the standard model. For example, by the well-known system mechanisms for type 1, type 2, type 3, blah, blah, blah. And the third one is that the dark matter. Dark matter, of course, it cannot directly related to Higgs, but it can also be related to the Higgs. For example, the well-known example is the Higgs polar dark matter. And the final part is, the matter symmetry. Matter symmetry, it's explained by the baryogenesis. And this must mean that we should incorporate some other physics about Higgs, for example, extend the Higgs sector or some new coupling to the Higgs. So all in all, almost all new physics may be closely related to Higgs. So this gives a very strong motivation that we should do something about Higgs, especially by search for Higgs and the signature containing Higgs, not Higgs alone. So after discovering the Higgs, what is next? We know the next step, maybe we have to is about the precise measurement on the Higgs coupling. For example, the tree-level coupling, HVV and HFF. This kind of tree-level coupling is very sensitive to Higgs mixing. This is the tree level. And the second is the Higgs to gamma gamma. Gamma gamma is very sensitive to charge the new particles. If the charged new particles coupled to the Higgs, it can change the Higgs to gamma gamma rates from this diagram. And this part maybe it's not that well known, but for the people that is interested in the Higgs, this is very important. It's about the Di-Higgs. Actually, the previous talk, Professor Chen talking about this search, Di-Higgs search. This is aiming at check the Higgs potential. Exactly speaking, is the Higgs self-coupling number HH, and the standard model is predicted with this number. And yeah, this is a Feynman diagram that producing the Higgs. We have two diagrams, mainly. This coupling. This is the unique diagram that the self-coupling enters, and this is the box diagram. But these two diagrams actually destructively interfere with each other. And yeah, somehow the conclusion is that only at the end of LGC we can probe this coupling, number HH. So here, after his discovery, we have to precisely measure the Higgs coupling and the Higgs self-coupling. And so what is the next to next? So of course, this is about the new physics. And the next, maybe here is some examples. The signatures with the Higgs are very expected in new physics. For example, the boosted Di-Higgs from resonance production from QQ or GGS to a pair of Higgs, and this is somehow it's interesting because after some result that the LGC search for Di-Higgs shows some excess, and I will comment about this channel. This channel is also very important for the Higgs self-coupling measurement itself, because usually this 4B channel, yes, Higgs to BB, as the previous talk said, maybe Higgs to actually the Di-Higgs channel may have a good chance in the BB gamma gamma and the BB tau channel. And usually the 4B channel is believed to have no chance to be probed, because this is a pure hadronic channel, and it has a big QCD background. But this paper just shows that if we consider the boosted Di-Higgs region, actually we have a chance to get something sensitive to this channel, and then combined with the BB gamma gamma and the BB tau channel, at the end of HC, we can even reach the level about within 20% at 90% CL, and in this case, even a small new physics effect that shows up in the self-Higgs the coupling can be probed.
But if it's boosted, then we will not be able to measure experimentally with the Higgs to gamma gamma final state, because we cannot know whether it's a single photon or two photons.
Another kind of thing. Because it's boosted, you mentioned the 4B channel. 4B channel. Yeah, because this is the largest branch ratio, right? Yeah, not the BB gamma gamma.
Right. Okay.
Okay. Yeah, so I will turn to my signature. This signature is boosted Di-Higgs plus MET. So first I will give a simple motivation why this is signature. At the one hand, searches for boosted Di-Higgs will carry out. I mean, yeah, because that paper showed that it's possible to search this channel. And I think maybe the experimentalist will carry out such a kind of search. So on the other hand, missing energy, for example, in the dark matter, the neutrinos, is well expected with the Di-Higgs in new physics. Later I will show a lot of examples. So we propose this incidental signature. I mean, incidental signature means that somehow it's just by the way, yeah, if you are searching this channel, so you can just carry out a very similar search, and then you can get a lot of information. So I just call this incident signature. And here is a simplified model for this signature. Oh my God. Yeah, the signature, actually, we can have two kinds of simplified model. The first one is that the missing energy is played by dark matter, and then in a lot of model you can expect that actually there is not only one dark state. You have a lot of dark states. For example, this is a very simplified model. Higgs coupled to the dark matter, and the heavy dark matter. This is a fermion dark matter. This is a scalar dark matter. And the second class is that the missing energy is played by the neutrino, and then you can expect that the Higgs coupling to a neutrino, and there is somewhat like a right-hand neutrino-like coupling, right-hand. And so in this case, actually, Chi2 can decay to H plus Chi1, and the Chi2, yeah, I will show this page. Yeah, like this, and how to produce this signature. And for example, we have two ways to produce Di-Higgs plus missing energy. If this is the first that the Zhaofeng process, and you can imagine that the Chi2 and all Chi3 in the dark sector is charged on the SU2 air, and then you can via Zhaofeng process produced, and then the Chi2 decays into the dark matter plus Higgs, and then we can have this signature. The second one is that it's similar to the Higgs-gluon fusion, and you can introduce, or you can have a new resonance in the model, and then you can pair produce from Chi2, and then you can still have this signature. And anyway, this is the simplified model to produce the Di-Higgs plus missing energy. And yeah, the background for the Di-Higgs boson, boosted Di-Higgs boson plus MET. The main background is the QCD4b and plus ZBB. They are irreducible background, and the second background is the reducible TT bar background. The TT bar is very large, but actually only the semi-leptonic modes with one lepton missed or misidentified as a jet, and the B jet may, yeah, I mean in this channel the 4B jet may from the mistagged light flavored jets. Actually, in this case, the missing energy is also from the detected effect, because the limited defect resolution, so you can have a missing energy eventually. So in this case, actually, this signature, I mean, the background somehow is the same with the boosted Di-Higgs, and the only difference is how to produce the missing energy. The missing energy, in this case, yeah, this is the dominant QCD background. It's from the detected resolution. And we can have a look at what is the power of Di-Higgs tagging. The Di-Higgs tagging, yeah, in our simulation, it's the Higgs tagging, the boosted Higgs tagging, the efficiency is about 20%. And if you have two Di-Higgs tagging, you can see this. Of course, this depends on the mass of the mother particle. I mean, the heavy dark Higgs states in the simplified model. If it's relatively heavy, for example, it can be heavy as 500 GeVs in this case, you can see almost all the background can be surprised. Only the QCD4b background is robust. Somehow it still can be comparable or even larger than the signature. So this is the case in the Di-Higgs, boosted Di-Higgs. Yeah, this is the power. And so we know if in the new physics, the large missing energy can be very powerful to surprise the QCD background. So it's easy to imagine that in this case you can use our missing energy to handle the QCD background, for example, large MET, because we are considering the pair production of the Di-Higgs. So probably the MT2 can also be used to surprise the background. And this is the result. And we show the result in this line. And yeah, this is the model particle mass in the unit of GeV. And this is about the production of the Di-Higgs cross section. You can have a look. You can see that if the mother particle can be as heavy as about I would say 1 TeV, the cross section can be as low as 0.1 finger-bar. So this is a quite powerful probe to new physics. I mean, that's the result of somehow the model-independent analysis. And now we are back to models. So here is actually this is the original motivation for my considering such a signature. I mean, in the dynamic type 1 seesaw mechanism. Here is the seesaw mechanism. You can see that if you are considering the right-handed neutrinos has mass originate in a coupling to somehow a Higgs-like field. I mean, it's not a Bell mass. You have to generate via a Higgs-like mechanism. And then you can expect that the Higgs can mix with the standard Higgs, and this way the right-handed neutrino can be produced via the gluon-gluon fusion process. And the right-handed neutrino can decay. Yeah, this is the second largest branch ratio of right-handed neutrino decay, because this is the goes-down equilibrium theory. Tells you that the right-handed neutrino actually dominantly decays into WW, and to Z and to Higgs equals, and the branch ratio is fixed about 1/6. And in this case, and we can have in this model we can find the sensitive in this line. Of course, it depends on the mixing angle between the heavy Higgs and the standard Higgs. I have taken it as the largest mixing angle, sin theta equals to 0.4. In this case, you can probe the right-handed neutrino about 500 GeV. I want to stress that actually probably this is the unique way to probe seesaw mechanism, because the right-handed neutrinos are singlet in the standard model, so it's very difficult to be produced in the standard model process. And maybe some people may believe that the right-handed neutrino can have a very large mixing angle with the active neutrino, but I think that must be quite fine-tuning about the flavor structure of right-handed neutrino. This is the second model. The second model is about the neutrino system. Yes, in the supersymmetry, it's very popular. In supersymmetry, we can see that there's a lot of models or examples to show that Di-Higgs boson plus missing energy. This is an example. For example, in the Biner-Higgs limit, and in this limit, we have 3 neutrino states, the Biner and the HD, HU partners. And if we are considering mu is quite larger than the Biner mass, and we get a Schur-Dirac particle, Schur-Dirac Higgs inner, and in this case, the Higgs inner can decay into binary plus standard model Higgs. Of course, in this case, the Goldstone equilibrium theory works again, and this is the result. And the conclusion is that probably you have to require the Chi2 decays to standard decays to Higgs plus the LSP, and the 2Z plus LSP have roughly equal branch ratio. In this case, you can get the largest signature rate. And here are some other examples. For example, yeah, I think I don't have much time to talk about it. For example, if this neutrino dark matter, in this case, yeah, if the right-handed neutrino is the missing energy, and the left-handed neutrino can be the decaying particle, and can decay to the standard model, the Higgs boson in this way, and this can be pair produced, and this serves as the scalar dark matter example. You can generalize this case to a lot of models. For example, doublet plus singlet and triplet plus singlet, and blah blah blah. And the NMSM example also show this kind of process. For example, this is lambda S HUHD, and in this case, the signature can decay into the standard model particle plus HU. The Higgs. I'm talking about it. In this case, the Higgs signals are much lighter than the signature. So yeah, you can. And then this is the singulator in the standard model, so you can expect that it can couple to the some new boson. For example, the singlet boson, and from the gluon-gluon fusion processor to produce this signature. And the third example is that the LSP is gravitino, and then in the Higgsino gravitino system, we can also produce this kind of signature. This is missing energy. And there's also an unconventional scenario, the stop system with a stealthy stop. The stealthy stop, in this case, the stop one escaped from the detector because it's degenerated with the real LSP or from some other mechanism. Anyway, it's the light stop just behaves as a missing energy in the LTC detector. So eventually we have this signature. We can only probe stop 2. Stop 2 can decay stop 1 plus standard model Higgs. In this case, it benefits in the large protection because it carries color charge at a strong. Okay, here is my conclusion. If the experimentists are going to probe the boosted Higgs boson in the 4B channel, please add one more single color, missing energy. And this signature is very expected in new physics, where missing energy may be a neutrino or dark matter. In particular, it may offer the unique chance to probe seesaw mechanism. And the third is the discovery limit can be as low as 0.1 finger bar at the end of HC, corresponding to right-handed neutrino and the Higgs signals about 0.5 and 1 TeV respectively. Exactly.
Okay, thank you. So we still have a lot of time. Questions?
Yeah, several questions. So now your scenario rely on the structured analysis, which means that you want to take the Higgs boson.
Yeah.
But what's the efficiency here?
You mean the B tagging efficiency?
The Higgs efficiency.
Yeah, I'm talking about it, but maybe 20%.
But that's
Yeah. Actually, you have.
For each one.
Yeah, each one. Actually.
For each one is 20% or 2 is 20%.
One.
One is 20%.
Yeah, maybe worse than that. Actually, you have to lose about 2 magnitude of.
Right. So you just assume, or you.
We have, in the simulation, I think it's input.
Well, but it depends on, so for instance, how boosted this Higgs is.
Yeah, of course, you have to optimize the cuts, for example, the cone size are, and
so
yeah.
First of all, you have to take the fat jet, then.
Yeah.
If you take only 500 then Higgs is 125. Then how percentage of the Higgs in this event get boosted?
Sorry. Yeah, I mean, somehow, actually, this is a show. You have to tune this parameter. I cannot remember not remember because this part is not my work. It's my collaborator. Anyway, he has worked on this part very carefully. He has to tune a lot of subject parameters, the delta R and some.
So this is a delta between two Higgs or a delta between two B jet.
2B, the fat Higgs jet, fat Higgs jet.
2B jet.
Yeah, 2B jet.
But the Higgs is very boosted, but how can the delta R is so large?
Small actually, it's 0.5, no, in this case. You mean it's quite large?
It's quite large in terms of boosted object. For example, when we look at the gamma star boosted into the two photon, actually the delta R is close to 0.
Right. So in order to use this boosted means that you have to the decay project.
Yeah, I see.
So delta R is very small.
Yeah.
Then you use the subject analysis to take down this.
Yeah, of course I know. But it's smaller than 1. You mean it's very large?
Well separated.
Yeah,
is,
one is well separated.
Not more than 0.5 is well separated if you do analysis. And anyway, I just curious about this.
Yeah.
So 20% you just assume, or you have the analysis.
Master analysis.
But if it's larger than 0.5, then the efficiency will be 50 to 60%. The tagging efficiency.
You mean the Higgs tag?
Because right now in experiment, if you have a single V jet, a well separated V jet, the tagging efficiency 50 to 60%, and the delta is greater than 0.5.
Okay, I will ask you more about that. Thank you.
I think here is that from the very statement, this delta R probably is the R parameter for the fake jet.
Yeah.
Not the delta R between this B, I think.
Yeah. Anyway, this is the cone size of the fat jet.
Right.
Maybe misunderstood something.
To form the fake jet.
Yeah.
Okay, the second question is about the stop 2, decay to stop 1.
Oh yeah, in that case, that's how to say it, that's a sad comment.
Okay, yeah. The more previous one.
Oh yeah, I see.
Okay, so here you say this stop will behave like as a missing energy.
Yeah, somehow.
Well, how come? Because it decays to top, right?
Because sometimes it can be degenerate with the LSP. So I mean, yeah. So the other final states are very soft, so they cannot be detected.
Final state, you mean the top?
Yeah, the visible particle.
Top plus LSP.
Yeah, top plus LSP, but top decay.
Yeah, because if
The stop mass is the same as top plus LSP. So
yeah, official, it should be official. Of course, official.
It's
very decay. So anyway, there are a lot of mechanisms to show stop 1 may escape from the LGC. So just add this side comment. This is somehow it's interesting.
So any other questions?
In this case?
Yeah, the Riemann black guy is the LSP, right?
Yeah, somehow like it.
But my question is, usually for type 1c, so we add the Riemann mass.
Yeah.
So usually, I'm thinking I would say that N will be much heavier than the stage.
That depends on the model parameters, of course. You can make it light. Yeah, because it's a low scale seesaw. I mean, this is the LSP. And this is the NLSP. This is the unique decay channel for this guy. So, I mean, of course, in this case, like this parameter may be surprised about the small Yukawa coupling, right? If right-handed neutrino is about 10 GeV or even lighter, and the Yn is very small, but it's not a problem because you have no other decay channels.
Okay, so yeah, let's thank Zhaofeng.
Okay.